what's up, YouTube? How's it going? We got another day practicing representation theory of finite groups. So we are currently in our algebra week. This is a daily live study session. I'm just going to be practicing, taking notes, hanging out, chatting with people. So this is kind of like an office hours even. People can ask me questions in the chat. This is not the basic math series. For those who are interested, we've got a bunch of newcomers. Like, holy crap, my first video just hit 200,000 views based off of this book. This video is not for that, but I hope that it's still entertaining and interesting potentially to the people who are following for this. So even though the math you might not understand, you still might get a vibe. You might get a vibe for what this type of math is like. And if you study this, then someday you can study this. They're both yellow books, and the yellow books, it's a very good brand. You can trust the yellow books are serious, real math books. Hey, what's up, Vob Edits? How's it going, man? How are you? Okay, so yeah, we're gonna get started practicing. We're in algebra week. Right now, the primary focus is representation theory with this book. But something that's new about, I think, my stream and how I'm thinking of structuring everything is that in Algebra Week, I will also be working through other books as well. So every now and then, I'll start doing some simpler exercises from Intro to Abstract Algebra, as well as some exercises from linear algebra, especially vector spaces. This way, I can get a mixture of like graduate level subjects with undergraduate level and maybe even high school algebra as well. And then next week, we're going to be working on foundations. This book is the primary book for foundations, for basics, but there's also harder books, and I might start adding in some tougher books like Enderton, Mathematical Introduction to Logic. I'm thinking of like maybe adding in some math logic, or maybe the goal of type theory, types and programming languages by Pierce. So I might mix in some harder foundations problems and books, but the primary focus of next week will be back to high school math with basic mathematics. Then the week after, we'll be doing number theory with the is algebra week all the way till Sunday. I typically only stream on weekdays, but if I do stream on the weekend, I'll play it by ear. Generally, like I'll make a decision as I feel like it on the weekends. So on Saturdays, I do a stream on basic math for the hobbyist members, and then sometimes if I stream on Sunday. Like if I only hit 3 or 4 streams during the week in the subject, I'll do the previous subject. But yeah, this Sunday probably not algebra, I imagine. But what's up, Arad? How's it going, man? And woo, logic, yeah, LOTR gamer. Yeah, I would love algebra week is greater than Shark Week. Yeah. I mean, I think it might be a nice way to kind of structure my practice sessions and me studying math truly for myself as a hobby and actually living by that ethos that for fun, I am studying and learning math. I'm not trying to become a mathematician. I'm almost certainly not going to contribute anything to mathematical research, but I still just enjoy it as a puzzle, as just a thing to study for itself, because it's better than TikTok. What's up? Rimmer Arnold J. They asked this stuff on my astronavigation exam. Cool. Which stuff? Are you talking about basic mathematics like this? Or representation theory? How's Luna? Luna's doing good. She's chilling. She's back there. Kaya, too. You can barely see her. Do you see this little bit of black fuzz around here? That's Kaya. She's shy. She's shy. She doesn't want to be on camera very much, but she still wants to hang out with us a little bit. I've got a sneaky cat back there. Kaya's doing good too. She's a little jealous of Luna and how much fame Luna has. What's up, int main void nil? How's it going, Divya? Okay, so let's get started. I'm excited. We're going to continue with algebra, with representation theory. And of course, these topics blend, like especially algebra and number theory really blend together. But still, like, I think it makes sense to separate these. In the number theory week, we'll primarily be focusing on elementary number theory, pre-algebraic number theory. Yeah. What's up, Luna? Calm down. Okay, so let me make sure my iPad is up on screen. Let me get the iPad on screen. How's it going, everybody? How's it going? Yeah, I think I'd really love to add logic into the mix. I think that would be really nice for myself. But the goal is that I can still primarily continue with basic mathematics, because that's what a lot of people are here for, and that's what I want to be practicing and teaching, like learning how to teach. Anyways, all right, so yesterday in representation theory, I began the definition of a morphism. And so a morphism is a morphism from a function to a function is a linear map between their vector spaces here. A morphism from these two representations, from one representation to another, is the linear map which commutes, like a linear map which commutes between the two vector spaces. So we have this diagram, and this diagram commutes. So you can take either path, like V down to W, over to W, or V to V, and then down to W. Either path from getting from the top left corner to the bottom right corner, either path is equal. So that's what a commutative diagram says, or a commutative diagram is about. Yeah, what's up? What's up, everybody? So we got that definition, and we got to this remark, and next we have a proposition. And I remember that this next proposition is going to be about the image of a morphism. The image and kernel of a morphism are subrepresentations. I think that this is it. Can I join in? I don't know anything about representation theory. Yeah, of course. What's up, Plaid Chart? Yeah, this is a study with me stream. It's really study with me. You should study whatever you should be studying and just hanging out. And I'd be happy to try to explain some of these things, even though you don't have any prior experience. Yeah, I'd be happy to try to explain some stuff to newcomers. The main one that I'd show is that you can rotate a square. You can rotate a square 4 times, and then you start repeating the same square. So then if I rotated one more time, then we come back here. And then for any of these, you can flip the square across, like maybe a vertical reflection. So you can flip the square 1, 4, 2, 3, 4, 3, 1, 2, and 3, 2, 4, 1. And this bottom cycle, notice that it is itself rotations, the same way that the rotations that we have 4 rotations in the top row. There are 8 symmetries of the square, 8 rigid symmetries of the square. And those are all 8 of them. And you can represent them by these matrices. A rotation matrix, what is this again? I, negative I, and a reflection matrix, which is this. So, therefore, I took something very abstract, which is this idea of a group of symmetries. And I can convert it to something concrete, which are complex matrices. Complex 2x2 matrices. These are much easier to understand. These 2 matrices are way easier to understand than these rotations and reflections. And I'll leave it at that. But there's my intro to representation theory. We have an abstract idea of symmetry and understanding symmetry as a mathematical object, and we convert it to something much more concrete and easy to work with, which are matrices. So plaid chart, let me know if how you feel about that as an intro. Did you get a vibe for what this topic is about, or did I just confuse you completely? I approve of all the math content on YouTube. There's not nearly enough, dude. There should be way more math content on YouTube. There should be way more. Many more streamers, specifically. I think that there should be many more math streamers out there. What's up, hexadecimal divorce? I'm sorry about the divorce. Okay, let's keep going. Cool, I liked it. Perhaps it requires linear algebra as prereq when dealing with matrices. Yeah, it does require some linear algebra prerequisites. So, unfortunately, you have to start somewhere. Like, this topic really does require some linear algebra, but you'd be surprised. You can learn it along the way, and I can teach some of those ideas as we go. But yeah, nice to meet you. Main goal here is to just hang out and chat math and whatnot. You don't have to understand the math that I'm actually working. Also, get me to do some push-ups, everybody. 10 likes, 10 push-ups. So hit the like button if you want me to do some push-ups. And let's see how many we can get. Cool. All right, so I'm now in chapter 4, and this is hard stuff. This is graduate level math. like straight up. So I think that this is the next proposition. Let me write it formally. The kernel and image of a morphism of representations are subrepresentations. Is like the idea, but then to state that formally, we have this. Let T be a linear map which is in the set of morphisms from phi to rho for two representations, phi and rho. Then the kernel of T is a G invariant subspace of V, and T of V, which is the image, also known as the image of T, is a G invariant, is also a G invariant subspace of W. Okay. Shall I try this one before I read the proof? Let me try it. What? Okay. So the kernel of T is a set of points V such that TV equals 0. And remember that that 0 is in W. So to show kernel of T is G invariant, which we can use some shorthand notation to mean to show that kernel T is G invariant, which can be written in shorthand as G kernel T is a subset of Okay, so the kernel of T, would be a subset of V. Well, of course it's a subset of V. It's a G invariant subspace of V. Oh. If it is G invariant, then G kernel T is a subset of kernel T. So any transformation in the kernel, or any vector in the kernel of T acted on by any group element is still in the kernel of T. Okay, so we must show for all vectors in the kernel and for all G in the group, phi G times V remains in the kernel. And we can think of it we can think of this as G acting on V. Like G acting on V, but it's acting on V by this representation. Proofs by LLMs, counterexamples take all the fun out of math, unfortunately. Yeah, well, I think LLMs will be particularly good at counterexamples, but I don't know. It's yet to be seen how good LLMs will be at creating new theory, creating new frameworks or new questions. It's yet to be seen. We don't know. Don't know yet. The thing is, like, for me, dude, my thing that I just keep harping on is LLMs have no impact on my learning of math. Like, I mean, okay, I can use it as a good tutor that's available at all hours. Like, instead of paying a professor to be my private tutor and grade my homework, I can ask LLMs to grade my solutions, and they, it's better than nothing. Even if it is not as fun as working with a human, I'd rather work with a human, right? But the fact that LLMs are going to be really good at math research doesn't impact me because I don't want to do math research. It doesn't take away any of the fun of learning math for itself. You can study math for fun. Like that, this is my argument that seems to be resonating with some people out there. Just because you're not trying to become a mathematician or an engineer or something doesn't mean that you shouldn't study math. Math can be fun. Like, just like why do you play a board game? Why play chess? Why play chess? Why play tennis? Well, okay, tennis might have other benefits, but similar benefits, like for health reasons, I think math can be a good thing for your brain, for the health of your brain. You might want to study math to keep your brain healthy, the same way that you play tennis to keep your body healthy, right? But then, okay, maybe, I don't know, chess. Chess might be keeping your brain healthy, sure. But don't people also just play chess because it's fun? Just because it's fun? Like, is there something wrong with just studying math because it's fun and that's it? That's the only reason to do it? Can this be represented by a visual diagram? Hard to get it. This stuff is kind of hard to, I mean, yeah, don't worry. This is going to, this is going to be a little trickier to draw a diagram for. You could, okay, so, I mean, I could try, but you're not going to follow everything here, and that's okay, especially if you haven't seen linear algebra. We do have these diagrams. So there's something called a vector space. Have you seen vectors, like regular vectors, yet? This is a generalization of regular vectors. These are vector spaces, which is a collection of vectors, thought of as a more broad type of vector idea. But you can think of Euclidean vectors, that's fine. We have a function from the vector space V to itself. So if I have a vector, it returns a new vector in the vector space V. Okay, in physics, you've seen vectors. Great. And then I have another function, which unfortunately we call rho, maybe for representation. And this is in a different vector space, but we have a different function in this other vector space. Now, a morphism says that we can either take this approach, which would be, we also have a function t, which will map from a vector in V to a vector in W. So t transforms from one vector space to another, and what the fact that this diagram commutes, which we draw with this nice backward curly arrow, means that if you take t after phi, so I can take this top path, or I could take this bottom path. I could take rho after t. Rho after t. Either way, this will get you the same vector. Both of these are equal. So if I applied this to a single vector v, either direction lands with the same value using these two functions in this order. So we typically just say t phi equals rho t. Now, the kernel, so t is this map between the two vector spaces. So t goes from V to W. The kernel of t is all vectors in V such that t times that vector is 0. So the kernel of t are all the vectors there might be many of them which all map to 0 in W. So every vector space must have a 0 vector, and there's a single unique 0 vector. But you can have multiple inputs that have the same output, and it's still a function. So the kernel is the collection of all of the vectors that map to 0. Well, if you take any two vectors in the kernel, then that means that TVI equals 0 and TVJ also equals 0. Then our linear transformation will then have this structure. So vi plus vj is also in the kernel of t, because vi plus vj maps to 0 as well. You may be confused about this step here, how I split it into two separate additions. That is a requirement of t being a linear transformation. For any linear transformation, you can factor out scalars. Well, first off, you can split addition which is the only property that I used so far. And you can factor out scalars. You can factor out a scalar multiple of the vector. So these are kind of two different properties, and I use the first property right here. So therefore, if vi and vj are both in the kernel of t, then their sum, vi plus vj, is also mapped to 0. In other words, the sum vi plus vj is also in the kernel. Now, so now our goal is to show, we want to show, if I want to say that this thing is in the kernel of t, we want to show that t of phi gv equals 0. That's what it means for this vector phi v to be in to be in the kernel. Okay, so that was a lot of info. I don't know if that made any sense. I hope if you just got like a little bit of a idea of this, then I would feel pretty accomplished, honestly, because to try to explain some of this stuff to somebody who's never seen it before at all is not easy, I think, because this topic is requiring a lot of background knowledge. So if you understood anything of that, I'd be happy. Is it that we need to prove that distance between vector space from both directions are same in magnitude, but there's a catch that kernel T of all vector spaces are 0? Am I right or off? I think that you're getting some of it. So vectors you can think of as having a direction and a magnitude, right? So I think that you're thinking of like the length of vectors and the distance of vectors or something. It's not quite that. That's where you're thinking of that part. It's more about like for any function, like there are special functions that preserve structure in some way. Like a linear transformation, like this thing here, it preserves the addition structure, because if you add two vectors or multiply them by numbers a and b, this might be more clear if I used v and w for vectors, but I used x and y as vectors and a and b as scalar numbers. this preserves linearity of addition. And then the second point is saying that it preserves the structure of linearity of scalar multiplication. So this is one example of a structure preserving map, or a structure preserving function, or a structure preserving map. Map and function are kind of synonymous. And so what you're describing, sometimes what you're describing is more closely related to something called the inner product. And what you're describing is actually really interesting because in physics, you've probably seen the dot product. You said that you've seen vectors in physics. Another way to write that, which is common, is with angle brackets instead. And the dot product is like the standard inner product. But the inner product has there's other alternative dot products that are more abstract, that have the same algebraic structure, like the most important properties. Let's see. The inner product is let's see. It's a generalization of the idea of the dot product. And we get ideas like the inner product of a vector with itself is the length of the vector squared. So this is magnitude, the idea of magnitude, or length, magnitude. And then a special linear transformation are those that are called unitary, which preserve the direction and lengths of vectors. So I think I'm probably giving you more questions even than, like, every time I'm answering one of your questions, now this might be creating new questions. But this is another structure preserving map. It preserves length. Oops. So in this, I'm saying that U is a special linear transformation which preserves length and direction of vectors, or the angle between vectors. Really the length and the angle between vectors. So this stuff it's kind of crazy, and I'm learning a lot of it for the first time myself. But the key thing, and this might be the place where you may not be able to catch up with everything else, but we are interested right now in these functions that preserve some algebraic structure. Another example that we see again and again in abstract math is the idea of a homomorphism. A homomorphism is something that preserves an operation, like preserves multiplication, or it preserves addition. These are called homomorphisms. And what I'm studying right now is the idea of homomorphism of representations. So this is a structure, again, a structure preserving map. Again, structure preserving maps where these things are both representations. And again, a representation is essentially the idea of converting an abstract collection of symmetries and being able to write abstract symmetries as matrices. Like, that is what a representation is. And so what I'm studying right now is if you have two different representations, two different ways to write down a group, or two different ways to represent symmetry as matrices, that there's a way to convert from one to the other in a way that preserves some important structure. Cool. Awesome, man. Dude, thank you for the opportunity to try to explain in like really a non-trivial way what I'm doing. I'm not getting into all the details, of course, but I think I'm doing a decent job right now of trying to get to the heart of what this math is about right now. And I'd be very curious for those in the chat, like I don't know if Arad or LOTR are still here. How did I do? Because it's not easy to try to understand, to try to explain some of this stuff that requires a lot of background info. And even if I'm not describing all of the precise details of exactly what structure preserving means everywhere, like there's still, I think that I'm able to convey the idea, the basic idea here. I liked your explanation. Well, hell yeah, dude. Thank you. Thank you. And if I could give you one last much simpler example of something here, if I could give you one last one, I was talking about the square and how you can flip it. Like if I flip the square along this vertical axis, we get this, right? And then if you flip it again, then you just go right back to the original square, right? You did great, much better than any of my professors, lol. Hell yeah, dude, that makes me feel very good. Thank you. Plaid Chart might be like, no, he didn't. I have no idea what he's talking about. But if you understood any of it, like, I think that's an accomplishment, because this is truly some graduate level math stuff. Okay, so what I'm trying to show right now, if we call this first one E, and the second square is S. E, we use, it's kind of like 1. It's like the original square, and then this other square is like you just flipped it. I have a sticky note here for this. Flip, and if you flip again, you're back to where you started, right? You can represent that by -1 to the n, right? If you have 1 and then you multiply 1 times -1, that's -1. And then if you multiply -1 times -1 again, well, -1 times -1 is 1, so we just stay in this loop. And we keep going back and forth for all time. 1, -1, 1, -1, 1, -1. So you can represent flipping a square as multiplication by -1. If you've seen if you've seen complex numbers, rotating a square is like multiplying by I. So 1 is just 1, or E, the original square. Original square E is the number 1. Rotating by 90 degrees is multiplying by I. So if you rotate by 90 degrees twice, that is I squared, which is -1. If you rotate 3 times, then this would be -I, so -1 times I. And if you rotate a 4th time, we have -I times I, which is -1 times -1, which is +1, and therefore we loop. We're back to where we started. So I would scratch this out and say, now we loop forever in a 4 cycle. So you can represent a rotation by the complex number I. And that creates a 4 cycle. And you can represent a vertical or any reflection by multiplication by -1. And this then creates a 2 cycle. -1, +1, -1, +1, etc. Hexadecimal divorce. Thank you. Thank you. I appreciate that. All right. Thank you. I really enjoyed that opportunity. Thank you for asking. All right. Let's keep going. Appreciate it. I hope you enjoyed. It's like dealing with the number of times it flips or rotates. Yes, exactly. Number of times that it flips or rotates, and you can count them all. If every arrow is R in the top row, then this, maybe I name the squares in blue. The original square, like a perfect Rubik's Cube before you do any rotations on it or something. The original square is E. If you rotate it once, we call this one R, and we've rotated 1 time. If you rotate again, this one is R squared. It's this orientation of the square is now 2 rotations. This one is R cubed, 3 rotations. And then if you rotate again, then we come back to E. So, the square, I'll say this in a second, it's generated by rotation. Like 4 rotations is the original square. And this creates a 4 cycle, like looping 4 times in a row. Or after 4, we restart, just like multiplying by I. And then this one would be S. Now, here's something interesting. To get to this square, what we can do is we can go through this arrow and then down with this arrow. So you could do S after R. Rotate first and then flip. So then this square is named SR. This one is S. Let me label below for these. Then this next square here is S after 2 rotations. To get to this bottom right square, I can follow the top row, 3 rotations, and then a flip. And then we get there. These are all 8 rigid symmetries of the square. And then we can see some patterns in these, like if you do S again, then you can keep looping back and forth. So there's multiple paths to get to the same square, and you can create little equivalences. One thing that's interesting here is that you'll notice SR is not the same thing as RS. So doing first a rotation, then a flip. SR is down here. SR is the square 1, 4, 3, 2. But if we first flipped and then rotated, we first flip and then rotate one. I'm always rotating in the clockwise direction, but it's arbitrary. You could choose all of them to go the other direction. If you first flip, then rotate, first flip, then rotate. I write these like functions, like the rightmost one is the first thing you do, and then, 1 second. Notice that this square is different. 3, 2, 4, 1. 3, 2, 4, 1. So it's not commutative. SR is not the same as RS. And that's interesting. So we need to build a presentation of all these symmetries. R to the 4th is the same thing as S squared, and both of those get you back to the original square. And I can write R after S is the same thing as SR inverse. Or if I am specific about the square, RS, which I drew right here, it looks like I just drew a 9th symmetry, but 3, 2, 4, 1 is right here. Same thing. We already have this one, SR cubed. So this was not new. This one is not a new, different symmetry. So RS is the same as SR cubed. This is a completely rigorous, full way to write down the entire group of symmetries of the square. Oh, cool. Dude, you're starting a You're starting to take a rep theory course next week or two. Heck yeah. I'm studying it for fun, so it's really nice to meet you. Like, let's learn it together, dude. You could be a guest anytime on stream if you want. You should stream it. I see that you got a lot of football content. You got some soccer videos. You should stream your math learning. Okay, so plaid chart. I hope that this, like, maybe I've just given you even more questions. But this, if the last thing I can say and just land on in this little presentation to you, no pun intended. This thing is a presentation. Of the group. If the last thing that I leave you with on this idea, if your only takeaway is, wait a minute, dude, this looks totally different than any of the math I've ever learned before. This looks completely different than physics math. This looks completely different than calculus. It's because it is. It's completely different, and it's, for some people, much more beautiful, much more fun to work in. Proof-oriented, abstract, pure mathematics is just wonderful, man. For some people, it's just a fun thing to learn and study. It is incredibly useful, too. Like, this stuff actually is used in physics. Like, very much. This stuff is key. It's so core to, like, 20th century modern physics. So it's not just abstract. It's not just a puzzle. It's not just chess. Even though mathematicians study it just like chess. Like, we wish that it were just a game that's harmless and just fun. But the physicists and tech bros keep finding ways to use this math. And we're like, all right, well, that's cool. I didn't expect anybody to use this in the real world, but this stuff actually is useful. It's critical to crypto. like Bitcoin is built off of all this stuff. Dude, I'm not a fan. I do not like Bitcoin. I'm not a crypto bro. I'm not trying to sell you any coins, like a jcpractices coin or anything. But mathematicians study this stuff just because it's really pretty, it's really fun, and it feels like playing chess or something. And it's just totally different math than what people usually study in high school. And people think that, oh, I learned high school math, that's everything. No, there's so much more math out there. Cool. All right. Hexadecimal divorce. I do not use GoodNotes. I use Notability. I've never tried GoodNotes. I bet it's the same. The most important things are how I connect it to my computer, I think, because there's a lot of like Blackboard note-taking apps. Like even Apple has one. I've just used Notability forever. I like Notability, but I think any of the Blackboard apps would work the same. The most important pieces are OBS to construct the layout of the scene, like my camera over here, chat down there, iPad on the side. I use an app called Air Server on Mac in order to wirelessly transmit my iPad to my computer, so I can, I don't know, I just don't like being plugged in. Of course, I use Apple Pencil. And I feel like there's another important piece. Those are the main things, though. Yeah, Hardy would say that solving a chess puzzle is like solving a math problem, only not as relevant / general. Maybe Hardy was biased. Yeah, I was thinking of Hardy specifically when I was referring to that. I was wondering if anybody would pick up on that. Gold star to you. Hardy wrote this book, A Mathematician's Apology, which it's kind of a sad book. I mean, it's kind of bittersweet. It's a mathematician at the end of his life feeling like his work has no meaning in the world, feeling like the math that he worked on, his life's work, has no impact on humanity. And he's kind of grappling with that in a philosophical sense. But he justifies it to himself, and he justifies it to himself, and he believes that it's still morally good because at least it's not being used. At least the study of prime numbers will never be used to build a nuclear bomb. Like, at least his life's work is not being used to create weapons of mass destruction and stuff like that. Which is, yeah, like, as mathematicians, you expect that the work that you build, the theory that you're studying and building, is probably never going to be used for anything. And that's okay. At least it didn't hurt anybody. Like, at least you taught some freshmen calculus. Like, at least you still taught people basic mathematics. At least you were a teacher and you taught basic mathematics, which people need to learn. And at least the math that you've spent so much time on, maybe it'll never help anybody's lives, but at least it doesn't hurt anybody's lives. So it's kind of a, Hardy would say, have you proven it? I had left a few minutes ago. Oh, okay. No, if you want to rewind, I think that my little presentation was fairly interesting. If you want to rewind and see some of it. I was still going on about, because the last thing you asked was about counting the rotations and flips, and I gave a little demo of how you can show this is a fully precise formal way to write down this collection of weird symmetries. And this is called a presentation of the group. Hardy would say 1789 is a Ramanujan number. Yeah, I don't remember. Is that one from the Taxi? Which book should you use for grade 9? I think this book, man. Seriously, the book that I'm using in my basic math series, this will make you like a math superstar, but it is grade 9 math. Like, you can work through this book in grade 9 and you're going to be the best kid in class. But it is exactly the same math. It's just like a little more adult. It's like an adult version of grade 9 math. Like it's a little tougher. It's a little tougher, but it's the exact same math. Get this book. Affiliate link below if y'all want to help me, earn $1. Yeah, dude. And if you haven't followed, please do hit the subscribe button. I have a series working through that exact book. I don't know if you already know that. Do you know that already? mathcanbeahobby.com playlist for basic mathematics. Oh, look at this good cat. She's happy. She's happy. Yeah, bro. Nice to meet you. Nice to meet you. Yeah, interesting. Well, no, he wrote a lot of undergrad books. I mean, he wrote undergraduate calculus, undergraduate linear algebra. I think Lang was probably doing what I'm trying to do. The reason that I'm doing a whole video series on this book and spending my own precious time, hell yeah, dude, go read some math, get off YouTube. Linear algebra tips? I have so many linear algebra tips, it's not even funny. I bet Lang was wanting to learn how to teach basic math. Like, Lang has probably never worked in a high school. Lang was a serious research mathematician and incredible math pedagogue. He wrote many of the best. He wrote so many beautiful pure math books. But he was a college professor. You know, he was a mathematician. I don't think he ever worked in a high school. And I feel he was like, if I could teach high schoolers math, how would I teach high school math? That's the purpose of this book. Like, if a mathematician could run a high school math class, how would they run it? If they had the freedom to go off of the standardized test curriculum and run the classroom how they want to, how would they run a high school math class? That's what this book is. It's good. It's really good. Otherwise, I would pick a different book. Because that is my purpose too. That my purpose is, how do I learn how to teach high school math? Yeah, she's so cute. She's good. She's good. Her name is Luna. Luna! Alright, go away. Go away. Go away! Okay, I want to get back to making some progress here. Thank you for hanging out with me. Hope you all enjoyed my presentation. So we're back to building maps between maps. And I'm trying to show that the kernel of a morphism is G invariant. Well, what do I know? Aha, wait. Function composition is associative. It's not commutative. But this is the same as T Fiji of V is taking the top path in the square, which is the same as taking the bottom path through the square. And now this is the same as rho g of TV. And we know that V is in the kernel. So then this is rho g of 0. And a fact about homomorphisms and any linear transformation of any linear transformation is that any linear transformation maps 0 to 0. So then therefore the kernel of T is G invariant. Next, we show that the image of T is G invariant. Let then we want to show that rho G, in other words, G acting on W is defined as rho, the representation of that group element acting on W, which is rho. So since W is some image of some vector V, and now I can rewrite rho G as T phi V. And now this is the image of some vector V prime so therefore if W is in the image of the transformation, then rho G times W is in the image of the transformation for all group elements G. In other words, image of T is G invariant. And the proposition is done. Heck yeah. Did it. Where are we on likes? You all have to tell me if I hit 10 likes. Dude, we got 21 likes and nobody told me. You all are supposed to tell me when we get 10. Dude, I can't do 20 in a row. I don't like it. I don't like doing 20 in a row. I'm not very good at push-ups. Thank you. Thank you for 20 likes. If we get to 30, I'll do 10 more. I owe you 20 push-ups right now. You all are mean. Okay, dude, the last two there were a little wimpy, but we did it. Thank you. Thank you for 20 likes. Any questions? Training both brain and body. Good job. I know. Dude, I don't work out, bro. I have not done push-ups in like more than a year. But this is a way that you all are going to force me to frickin' try to actually hit some push-ups. Ooh, somebody's somebody represented me in the Math with Ming Discord. Hell yeah. That's awesome. Whew. Explain what kernel is. Yeah. I wish I had a decent example. Okay. What is a good example? I wish I could come up with a decent example of something with a non-trivial kernel, but if T is a linear transformation of two vector spaces, then it maps vectors to other vectors. In other words, we can write like a vector is mapped to another vector, like this. A lot of the functions that we're used to, well, one thing is that a linear transformation always maps 0 to 0, and the 0 object is different in V versus the 0 object in W. Projection maps, that's a good one. Okay. The universal property of kernels of no. Projection map, that's a good example. Yeah, okay. So, but there are transformations T such that TV equals 0 and V is not 0. An example, this is a great example, is the projection map. I'm going to say projection maps. There's two of them. Pi 1, I'm going to take R2 into R, and pi 2, we use pi because it starts with a P, which means is referring to projection, right? Pi 2 also takes R2 into R, where pi 1 maps to the first element, and pi 2 maps to the second element. So pi 1 times the vector 1, 0 is 1. Pi 2 of the vector 1, 0 is 0. So we're projecting to one of the coordinates. Notice here, this says that the vector 1, 0 is in the kernel of pi 2. And 1, 0 is not the 0 vector. So there are vectors, there are some transformations where you have multiple vectors that map to 0. Great call out, Locke. Thank you for that. Yes, a projection map is a great example of something that has a non-trivial kernel. We say that the kernel of a transformation is trivial if the only input that maps to 0 is 0. Because this is always true for any transformation. Any transformation will always map 0 to 0. And if that's the only one, then the kernel is trivial. But if there are multiple points, more than one, that map to 0, then the kernel is non-trivial. I don't think this question is related to the content, but it's just jumping into AIME problems directly better if you have already covered the syllabus, or is ramping up the difficulty better in practice? I would always recommend, it depends on your goals. Honestly, I think if you are ready to start thinking about AIME problems and you're interested in something like that, you should get a tutor. You should get a private mentor or find a study group locally. Join math club if you haven't already. But more important than thinking about what subject do you learn next, which book do you work on next, what, do you work harder problems from what you already are doing, or do you start learning new math? More important than that is find a mentor. Because the answer to that question depends on you, on your specific goals, on exactly where you are. You might have gaps, you might have blind spots, and you don't realize that you're lacking in some foundational things. Maybe you think that you're further along than you actually are. Sometimes we think that, I understand this material perfectly. I would, if you're thinking about trying to start learning AIME and you're starting to feel bored by your current work, find a mentor. That can be us here in chat. And I'll pause and answer some questions like this sometimes, but I'm not going to be able to give you one-on-one individual attention the way that a local tutor could. And then similar but different is find other fellow students. Find peers who are also try to find peers who are also interested in going beyond the syllabus. Why is the kernel always mapping to 0? Can't it map to other numbers? Yes, absolutely. And is kernel with one path to 0 is non-trivial kernel, but multiple paths are trivial kernel. The definition of kernel of a transformation is all of the vectors that do map to 0. A transformation, yes, can map lots of numbers or vectors to other things besides 0. The projection map that we already talked about. It maps 1, 2 to the number 1. It maps 0, 0 to 0, it maps 0, 1 also to 0. It maps 1, 0 also to 1. Right, so there are, and infinitely many more. There are infinitely many more, but pi 1, this transformation, this linear transformation, I should really put some dots or something to say that there's infinitely many more mappings. I just want to show that there's at least two. This is a linear transformation, whereas the kernel requires that every vector in the kernel maps to 0. It's very rare to understand any material completely, TBH. Yeah, like, definitely. Nobody understands anything completely. Nobody understands anything in math completely. The closest thing is linear algebra, but even linear algebra, we don't completely understand. I would say find a private mentor of some kind, and that could be your teacher, that could be math club, that could be me. Like, email me. If you want private tutoring, I am available as a private tutor if anybody wants it, and I'm much more affordable than other people in the US. But I charge US rates, but I guarantee you I'm cheaper than probably even a grad student. Like, I just really want to get reps. I want to get repetitions in experience teaching people one-on-one. So if anybody wants a private tutor, jcpractices@gmail.com. I could be your private tutor. Somebody just commented on my video from yesterday asking about this, so I want to take a moment on stream to write it. I am available for tutoring. One-on-one or group tutoring as well. But generally speaking, I would recommend going for depth. If I just gave you a yes or no answer to your question earlier, Girish, Miraj, Kar, instead of learning new math, I would do the math that you already know deeper. Like, reset, go back to the integers, go back to the basics, learn it all deeper. Like, learn it with more depth, more rigor, more mathematical maturity, instead of learning the next topics, like, at a shallow level. Like, instead of learning more math at a shallow level, go back and learn the math that you already know deeper instead. Because the basics, addition, numbers, prime numbers, that stuff gets really, really hard. Like, that stuff gets really, 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 really hard. You don't need to add the square root of 2 for math to get harder. You can learn really hard math just with integers. Yeah, to go further into kernel and the reason to learn the kernel, I don't want to detract. We've already kind of gotten off topic a bit. I would say if you want to learn more about the kernel, look at my linear algebra videos. I have a whole series of videos, like, dude, I don't know, 100 videos or something about linear algebra. The old ones are $1 a month membership, but the most recent 10, I think, are free. And in particular, you want to learn about vector spaces. This is the beginning of abstract algebra, and the kernel is a very important example of a subspace. It's one of our first examples of subspaces, and that's actually exactly what this proof is about that I just worked. The kernel is a subspace. The kernel of a G-invariant subspace is a G-invariant subspace. The kernel of that transformation is also G-invariant, so it preserves the structure of these representations. Yeah. So algebra, I think it's accurate to say that algebra is really about this idea of preserving structure, like maps that preserve structure from this object to this object. Cool. All right, so I worked that proof. I feel very good about it. I don't think I missed anything, but let me read Steinberg's proof to make sure I didn't miss anything. Let V be in the kernel of T, G in G, then T phi V is rho T since V is in kernel. Thus kernel is G invariant. Now let W be in the image, choose W equal TV, then rho W is rho TV is that, which is in the image of T, establishing that image of T is G invariant. Yeah, so I got it. Nice. His is just like a little more succinct and clear because it's refactored. Set of morphisms from phi to rho has the additional structure of a vector space, as the following proposition reveals. Proposition 415. Let phi be a representation and rho is also a representation of the same group into a different vector space. Yep. Okay. I believe this. So subspaces say that when you combine two elements in a set, then the combination of those two stay in the set. Like the addition of two vectors is still in the same subspace. In this, we're going to choose two transformations in the set of morphisms from phi to rho. So I think that we want to show that we have closure of scalar multiplication And we have closure of combinations. Like, and the combination is function composition. I don't think it's additive, right? Is it additive or is it function composition? Sup? How's it going, geometry? Yeah, I mean, I'm pretty sure it's. Oh, it has to be. It has to be because. Like, what is the. Oh, no, it couldn't be. It couldn't be. It couldn't be function composition at all. No, because. Yeah, it has to be addition. It's this. Because. Yeah, if both of these are mapping V to W, then it wouldn't make sense to take T of. You can't take T1 of an element in W. So the linear structure is that the addition of two transformations in Hom in the set of morphisms is a third morphism. So okay, so we want to show. Let's let V be in the vector space V. K is in, I suppose, everything. All our vector spaces are over the complex numbers, and I can check on if I can relax this to a field. But for now, K is a scalar. And let's choose a transformation in. Let's choose a morphism of phi to rho. Then KTV say linearity is the same as k of TV, wait, oh, we want to show okay, we're not going to get to anything here. That's just showing that the map is linear. We want to show that for all group elements, and for all vectors in V, that the commutative diagram is preserved. That here, let's refactor this just a little bit. We want to show that KT is also a morphism. And what that means is that T after phi, KT after phi is the same as rho after KT. To show this, let V be a vector, then KT phi G times that vector is because these are linear transformations, we can factor out the scalar. T phi G V. And T phi G is the same as rho T. So first take T and then take rho. And by linearity, I can rearrange the scalar multiple Yep. So KT phi equals rho KT, which shows that KT is in the set of morphisms. Similarly, if I choose two transformations after, if I choose two transformations, I show that the sum of those transformations is also a morphism. The sum of two morphisms is a morphism. So I do this after phi. This is the same as T1 phi GV plus T2 phi GV, and phi is the same as, or T phi is the same as rho T because we assume that T1 and T2 are morphisms. And now this rho T is a linear transformation, so this is rho G applied to T1V plus T2V, which is rho G composed with T1 plus T2 acting on the vector V. So therefore, we're done. So T1 plus T2 is also a morphism, and we are done. Yeah, I didn't really use anything about the fact that the scalar was a complex number. I just used the fact that it's a field element. I mean, this book uses the field is the complex numbers everywhere, but the second one can also be done point free. Oh, can it? Very nice. Thank you. I think I got it. Yeah, you must have caught my error about multiplying or like function composition being the structure. Not function composition, it would be element-wise addition. I think I got it. I think it would be function addition, right? Or yeah, element-wise being the elements are transformations. Yeah, I figured that out by the type checking as well. T1, T2 doesn't even type check. I fixed it. Hey, what's up, Johnny? How's it going, dude? All right. I think I got it. My prediction is that Steinberg likes to do these proofs as just one step, that T of C1 V1 plus C2 V2 equals C1 T V1 plus C2 T V2. Steinberg prefers to do them in one step, but I'm so used to doing these subspace proofs as two separate things, and I just feel it's cleaner somehow to just show that it preserves multiplication, and then it preserves addition, and then therefore it preserves both of them. I don't know. I like it better that way. So let me read the proof. I don't think I missed anything important. Yeah, he's got in like one line. Okay, so and he chose the scalars to be in the complex numbers specifically. Yeah. C1T1 plus C2T2 phi is that. Yeah, fairly simple. Writing the conclusion of the proof at the end of the proof is something I oscillate between doing and not doing. Yeah, I mean, I do too. I think that the square reminds you that the entire proof is done. But I like to reiterate sub goals. If you're talking about this, because this is just a sub goal. This was a sub goal of if this was G1 and this is G2 or something. I like to reiterate the end of sub proofs. And then sometimes I do like to just reiterate the conclusion of, or like reiterate the general claim. And so we are done. Therefore, what is it we just proved again? Therefore, the set of morphisms is a subspace of the set of homomorphisms or something. The set of morphisms of two representations is a subspace of the set of homomorphisms is a subspace of all linear transformations from V to W. Yeah, subproofs into paragraphs, at least on paper. Yeah. I mean, my paragraphs are kind of backwards. I like my paragraphs to be indented. I kind of screwed up my indentation on this one. But I do like a reverse indentation. Similar to coding. Like for each of my paragraphs, I begin, the first line is longer, and then everything else is indented, similar to coding. So this was like goal 1, and then this one was goal 2, or subproof 1, subproof 2, whatever we call them. Like that's my preferred style. Oh, Python's Lexer has an explicit token for dedents. So I'm talking about a dedent here? Is this a dedent? In the opposite of an indent? I love it. That's what I'm talking about. I'm talking about dedenting. That's cool. Awesome. Yeah, I love dedents. Cool. I mean, it sounds like it. I guessed it probably is. Anyways, yeah, it was fun to hang out at that Math with Ming stream yesterday. He didn't really want to chat very much about representation theory or, he seemed to be like, okay, great, nice to meet you. Let's get back to quaternions. We're doing applied math here. But yeah, it was cool to see his stream, and that's amazing that somebody shouted me out independently in his Discord. That's pretty cool. He's doing tensor analysis right now, like as we speak. That's cool. I don't know anything about that stuff, and I'm trying not to get nerd sniped. As a matter of focus, I don't think quaternions is going to help me right now. And so I'm the same way as him. Like if he came in and wanted to talk about quaternions, I'd be like, that's cool, but I'm focused on representation theory. Like very focused on the topic he does. Yeah, I get it. I get it. But anyways, it was nice to meet him, and I'll try to swing by a little more often sometimes. Have you seen Kay? Is Kay still streaming at all, or has he just been demoralized by that terrible experience of getting hacked? Freaking sucks. And yeah, quaternions are relevant for software games. Yeah. Yeah. See, it's too applied for me. Too applied for me, dude. Too useful. Sounds like you can make too much money with quaternions. I'm not interested. He hasn't streamed in 13 days. Dude, that sucks. That sucks. I want K back. I've been meaning to invite him on stream for a representation theory follow-up. I should be doing that. Unrelated, you've done 98 of SOA samples for one of your actuary exams in the past few days. Already took the exams. It's sort of a refresher. Nice. I don't know what SOA is, but actuarial exams are hard as hell, man. Good for you. Okay, so I feel good. I mean, those are simple proofs, but we did them still before reading the proofs. That's something I didn't do as an undergrad. I did not try to attempt proofs before reading them. I should have. Fundamental to all of representation theory is an important observation due to sure that, roughly speaking, morphisms between irreducible representations are very limited. Interesting. Okay. Thanks to this guy, this guy noticed that morphisms between irreducible So what does limited mean here? I'm imagining that means few in number, that they're rare, that there are few morphisms between irreducible reps. I don't think it means that they're like limited in power or something, that they're like not very useful. I think it's that they're rare. This is the first place where we seriously use that we are working over the field of complex numbers and not the field of real numbers. Okay. First place where we use our field is the complex numbers, not the real numbers. But what about others? What about more abstract? What about other fields? That's my next question. Namely, we use that every linear operator on a finite dimensional complex vector space has an eigenvalue. Okay. I see. I think I remember that. Every linear operator on a finite dimensional complex vector space, so we need finite dimensional complex vector space, has an eigenvalue. I think I need to relearn, find a citation on this one. Ooh, the field medalists have been announced. Hell yeah. Direct sums give you a lot of flexibility for what kind of maps you can have out of / into them. Yeah, I mean, that makes sense. Yeah. Irreps give less freedom. In general, you need an algebraically closed field. That's what I was first. That's where my mind went. Like that, this is algebraically closed, whereas the real numbers are not. Yeah. The closure equals itself. Of some nice characteristic. Ooh, opening ceremony is live right now. I'm not a reaction streamer. We could become a reaction streamer. I didn't saw that, but I knew 2 names would be there. I don't know anything. The last fact follows exactly because C is algebraically closed. Yeah. Yeah, this is where I'm missing some abstract linear algebra understanding. So I want to see, before I forget to do this, I want to see if I can find a citation for this in one of my linear algebra books. I know it'll be in Axler, and it sounds like it certainly will be in Dummett and Foote in the widest setting of modules in algebraically closed fields. I bet that Fraleigh also points out that complex valued vector spaces have an eigenvalue. This would be in chapter 9. Yeah, every n by n complex matrix has n not necessarily distinct eigenvalues, and it's a consequence of the fundamental theorem of algebra, which we stated in section 9.1. Yeah, this makes sense because you build the characteristic polynomial, and it always has solutions, or it always has roots, whereas a characteristic polynomial of a real matrix, you can easily build a real matrix which does not have roots in its complex, or in its doesn't have real valued roots in its characteristic polynomial. Okay, all this makes sense to me. Yeah. Yeah, it's just that this book did not make a big deal of this. It just did not, like, it just states it in the text, as in, like, of course. It just didn't really call out and make this like an important fact to realize. Not every linear transformation over real vector spaces has an eigenvalue, but every complex valued transformation does have eigenvalues. That makes sense. And this book has Schur's lemma in it, which is cool, because this is the same Schur as who's on my iPad right now. Schur's lemma. Let A be an n by n complex matrix. There's a unitary matrix U such that U inverse AU is upper triangular. So now we're getting to like real connections between these different books. Yeah. Okay. And then this just seems like such an important fact that I feel I should have been able to predict, that I want to see where the relevant theory is in my prerequisite books. And I haven't been reading Axler's treatment of eigenvalues, so I'm not too surprised. F denotes R or C. V denotes a vector space over F. A number lambda is called an eigenvalue of T if there exists V such that ... Okay, the word eigenvalue is half German, half English. The German prefix eigen means own in the sense of characterizing an intrinsic property. Nice. I always thought it was German. Now I know. Eigenvalue is own. It's like a self-owning vector. Operators, map of vector. So endomorphisms is what Axler refers to as operators. Product of polynomials, invariant subspaces, eigenvalues, eigenvectors. Is this an exercise? Just seems like such a important fact to realize that seems obvious now in retrospect, now that I'm thinking about it, but yeah, it's not. Okay, every operator on a here we go. Yeah, every operator on a finite dimensional non-zero complex vector space has an eigenvalue. So in Axler, this is in the section on the minimal polynomial. And this is Axler 5.19, existence of eigenvalues. And we need to remember it's a finite dimensional, non-zero complex vector space. Cool. And it again cites the first version of the fundamental theorem of algebra, that every polynomial has a root. The proof above makes crucial use of the fundamental theorem of algebra. The hypothesis in the result above that the field is complex cannot be replaced with the hypothesis that the field is real, as shown by example 5.9. Next example shows that the finite dimensional hypothesis also cannot be deleted. Axler builds the minimal polynomial. Eigenvalues are the zeros of the minimal polynomial. Not the characteristic polynomial. This is cool. Okay, I look forward to reading Axler. It looks really nice. It looks super nice. But I think I got the gist of this. And it makes sense to me now. The characteristic polynomial, and then there's minimal polynomial as well. Rotation doesn't have real eigenvalues. Yeah, that one was an example in this. That is so cool. Oh, the takeaway is that there are no rotations over the complex numbers / S. Okay. Neat. Okay. This is a consequence of the fact that every polynomial over C has a root. In particular, the characteristic polynomial of the operator has a root. Yeah, so this book reiterates the same ideas that I just went through as well. This is a consequence of the fact that every polynomial has a root. In particular, characteristic polynomial of the operator has a root. Lemma 4.1.6, Schur's lemma. And this is a very different Schur's lemma, but I guess it's maybe somehow equivalent to the other one in the other book. Lemma 4.1.9, Schur's lemma. Let phi and rho be irreducible representations of G, and let T be a morphism between them. Then either T is invertible or T is 0. Neat. I've been wondering this. Like, if you have a morphism from one to the other, when do we know that we also have a morphism back from rho to phi? Okay, so either you do, or the only one that does not have an inverse is the 0 map. Cool. Consequently, if phi is similar to, if phi is not similar to rho, then hom so if T is not invertible, T being invertible is the same as saying that phi and rho are equivalent. Right? And if phi equals rho, then T equals lambda I with lambda in C. So the only is this a typo? Should it really be phi equal rho? Should be similar. Are two similar irreducible representations equal? Was that a fact that I forgot? So two similar irreducible reps. Hmm. Or I guess maybe this is just a stronger claim or something. Maybe they're not. Maybe they don't have to be equal, but if they are, if T is invertible, then they are similar, or they are equivalent. So part A, I think is pretty clear to me. It's almost just straight from the definitions. And then part B, if the two are the same, then if the two are the same, then I think T must be invertible. And then because wait. I'm getting kind of tired. We're 2 hours in. Um, Let me read chat. Yeah, I've heard about the massive protest in India about there's some sort of academic dishonesty or something about an exam. Like people got a copy of the exam early or something like that. Like there's something about an exam that there's some like major like widespread cheating or something like that, and then a lot of people who took the exam honestly are being cheated, something like that, which is messed up. I mean, that's really messed up because those exams are so life changing, I know, and there's so much on the line regarding those exams. Yeah, I didn't think that two similar representations have to be equal. That felt just wrong, right? Yeah, part B is just a stronger version. Dim C is one. That's like the next consequence or like the next remark after this proof. Yeah. So Sundar, yeah. Man, I feel you, I guess, or I don't know what to say. Like it's pretty crazy stuff. I don't know much beyond that. I just know it's happening, but I haven't followed it at all. Y'all, we just need 2 more likes, and I can either do push-ups or play a song. How about that? I could play a guitar song or do push-ups if we get 2 more likes. I feel kind of tired. I think I've made some pretty solid progress today. I don't think I want to just read the proof. I feel like I should wait and tomorrow or tonight on my own try to prove this on my own before reading the proof. Like I think it's better to pause, stop, regain some energy, maybe drink some coffee and try to work this proof tonight before just reading the proof. I think that that's going to be a smarter way to continue than to just keep going right now. A lot of exam papers got leaked, and major exams on which country's future depends on, let alone a single person, like NET is given. Yeah, dang, dude. Yeah, that's crazy. Like, so the protest is like saying that everybody should that entire exam should be invalidated, right? something like that. It's crazy. All right, dude. Vote in the poll, everybody. I think we're close. We just need one more like. Vote in the poll. If we get one more like, should I do 10 more push-ups, or would you like to hear some classical guitar? All the background music. Oh wait, there's no background music right now. Why is there no background music? What happened? Okay. Well, my bad. I thought that there was background music this whole time. All the background music on this stream is me. These are my recordings. And I would be happy to play something for you all if anybody wants to hear a guitar piece. Or you could just beat me up and freaking make me do more push-ups. Either way, it's going to help me with my guitar, so I don't care. You get to pick. How would you rather if I improve my guitar a little bit? Push-ups, heck yeah, thank you. Thank you. All right, 100% so far. People want some push-ups. Let's go. Thank you, everybody. I've had a blast today. We did a lot of intro to group theory and representation theory. Somebody was asking about if I could explain the idea of the kernel of a transformation. What am I talking about? And I generally try to focus on the idea of linear transformations are structure-preserving maps, and algebra generally is often about understanding these maps that preserve structure. Like you have some mathematical object over here with some kind of patterns and some kind of structure, and then we find a way to convert from this object to this other object and keep some of the structure, some of the patterns and symmetries and things in this thing now are still being reflected and preserved over here. So linearity is a type of structure. And then another type of structure is symmetries, and like group symmetry, group structure. So I defined and I gave an example of the square and these rotations and cycles. We have a 4-cycle and a 2-cycle, and we can combine between those two different symmetries in a certain way. And these two matrices, these are numbers. They're much easier to work with. We can write them down, multiply them. We can find eigenvalues and eigenvectors of these. They capture the exact same symmetries as the square. Like the same exact 4-cycle and 2-cycle and this anti-commutativity property. The same non-commutativity relations hold. So I showed how other simpler cycles, like we can represent the vertical reflections as powers of -1, -1, +1, -1, +1. That's a 2-cycle. And then the powers of the complex number I, which is the square root of -1, this creates a 4-cycle. In a very real way, if you combine those two facts together and kind of glue them together, we can build these matrices. Hey, thanks for the star. I appreciate it. What's up, Fyodor Daniel? Thank you. So these matrices, combining these two matrices, preserves the structure of symmetries of the square. We talked about other structure preserving maps, including these unitary maps, which preserve length and angle of vectors. And we talked about the kernel being a type of map that maps everything to 0. We talked about the kernel being a subspace of a vector space. So that defines some structure. Like the kernel of a map has a lot of structure in it as well. And then we talked about how we are preserving some structure between, if you have two different representations, like two different ways to get from V to W, like we can relate phi and rho with t. In particular, rho t equals t phi. Rho t equals t phi. And that's what a morphism requires. And yeah, we got some lemmas and we worked a couple of proofs. Yeah, thank you. I did a lot today. I feel like I've made some progress. And I hope you all enjoyed it. Thank you. A lot of today was all about really trying to introduce somebody to what am I doing? What is this? I don't know anything other than calculus. And I tried to give kind of a rapid fire idea of what is abstract algebra all about. It is about understanding structure of mathematical objects and when can you preserve structure when you're converting from one object to another. Push-ups, hell yeah, dude. Thank you, everybody. It's been a pleasure. I will practice some classical guitar on the second channel, so if anybody wants to join me for that raid, we will do that. Give me a second. Let me set up the other channel, the other stream. I haven't streamed guitar in a week, I feel. So I've been neglecting my primary channel. So if y'all want to join, it's a nice little study with me kind of space. Like it really is a nice little group of people who are just, I don't know, hanging out. It's kind of like a radio show. It's really similar to this. It's deliberate practice in classical guitar. Hey, you already commuted and Dude is still at it. I'm wrapping up though. But we're about to do classical guitar next. So if you want to join me for the raid, for the redirect, would love to see you there. If not, no worries. Y'all, I had a blast today. Let me do some push-ups and then we're going to go practice some classical guitar. Thank you everyone for watching. I had a blast today, as always. Please do like and subscribe if you haven't already, and see you soon. Here's 10 push-ups. Let's go. Thank you for 30 likes. Okay, dude. I would give those an 8 out of 10. They were decent. They were pretty decent push-ups. They were decent. Not the greatest. You are out of camera. Yeah, I'm sorry. I don't have a push-up cam. I'm sorry. You just have to believe me because I'm like breathing a little harder or something. You just have to trust me. All right. Thanks for watching. Bye, everyone. Bye. What about now? I mean, I should be back now. Sorry, I'm not doing push-ups on cam. I'd have to set up a secondary camera, and that's boring. That's just lame. Thanks for watching. If you want to watch more math, here's my playlist of basic math. Math can be a hobby.com. If you want to see classical guitar, just in case the RAID doesn't work, here is my secondary channel. Yeah, those are the main things. If you want to see another math streamer, go check out Math with Ming or Leo Lectures. I don't know if Leo is streaming. You could also check to see if Math with Ming is live, Leo Lectures, or K-Theory. Those are all places you could go next. Thanks for watching. Bye. See you on the guitar channel if you want to join for that. Take care, everybody. Bye.